Mallory, Assistant Professor in the Department of Computer Science and Engineering. We can say a grammar is ambiguous if there exists one string for the language that are generated more than one parse tree. For a single grammar, if we generate one or more leftmost tree or one or more rightmost tree, we say that type of grammar as the ambiguous grammar. If For a single grammar, if we have a two parse tree, we prove that type of grammar as ambiguous. The method for fixing the ambiguous grammar are to set the precedence. We have to define the operation to execute first to avoid the ambiguity. Next, to define the associativity, specify whether the operation evaluate from left to right or from right to left. And we need to rewrite the grammar, breaking the general rule into a smaller and a higher specific one to enforce the exact hierarchies. Here we have taken an example. In this example, we need to prove that whether this grammar is ambiguous or not. Ambiguous is nothing but if we able to derive two parse tree, whether in the leftmost deviation or in the rightmost deviation, we say that type of grammar is ambiguous. Here we are going to take this grammar and prove we are able to generate two parse tree in the leftmost deviation. Then we can say this grammar is ambiguous. The string given is A B A B A B B. So as I said earlier, we are going to start with the start symbol S. Here I am going to take S equal to AAB. For A, I am going to replace with PS, and for S, I am going to replace with ABSB, and for S, I am going to replace with A. Here we got the string AB, AB, ABB. Simultaneously, for this deviation, we are going to draw the parse tree. I'm taking the start symbol S, then replacing it with AAB, and for A, I'm replacing with BS, and for S, I'm going to replace with ABSB, and for S, I'm going to replace with A. Here we got the string sorry, here we got the parse tree for the string ABABABB. Here I am taking the same grammar. I am going to prove this grammar as ambiguous by drawing another leftmost deviation and the parse tree for this grammar. For this, I am taking S equal to AB SB. For S, I am going to replace it with AAB. For A, I am going to replace with PS, and for S, I am going to replace with A. Here we got the string AA, BB, AB. First, I have choose A, B for the leftmost tree. Here I have taken A, B, S, B. So we can say this type of grammar as ambiguous as we got two parse tree in the leftmost deviation. For the deviation 2, we are going to draw the parse tree. First, I'm taking S and replacing it with A, B, S, B. For S, I'm going to replace with A, B. And for A, I'm replacing with B, S. And for S, I'm replacing with A. Here we got the string A, B, B, A, B. Pushed-on automata is a theoretical model for computation of recognizing the context-free language. It uses additional equipment for the memory structure of stack. As it uses stack, it is based on the concept of last in, first out. These stack memory are allocated in the machine to track the nested pattern and the standard state machines. We can say the push down automata based on the 7 tuples, where Q is the finite set of state and sigma is the input alphabets, gamma is the stack alphabets, and alpha is the transition functions, Q0 are the initial state, and Z0 are the initial start symbol, and F is the final state. Here in the stack default we'll have Q0, which is a initial stack symbol. In the stack we first push the initial start symbol when it is empty. How this push down automata works based on input tapes. finite control and the stacks. It contains the strings to read the input from left to right based on the input steps, and then the finite control, it processes the unit that can be transmitted between the current input and the top of the stack, and the stack maintained purely the based on the last in first out concept. When it find a matching element, it remove the element from sorry pop the element from the stack.